All right, in this video, we want to find the differentiability of this piecewise function, basically where it's differentiable and where it's not differentiable. So let's start with looking at the piecewise functions. The first thing we want to do is we just want to analyze the piecewise function. The first equation is quadratic for x is less than -2. Quadratic equations are continuous and differentiable everywhere, so that's good. Second one is a rational function, and we have a vertical asymptote at x equals to 0. And x equals to 0 is in between the given interval here, which means that the first thing we need to note is the function is not differentiable at x equals to 0 because it is a vertical asymptote. So we already found one point where it's not differentiable. If you look at the final equation here, we have a square root x here, which gives us a domain of x is greater than or equal to 0. But our interval is x is greater than 4, which means none of the negative values really matter for this one. So this function is also going to be differentiable everywhere. Now that we've analyzed the three individual functions, we have to compare where the functions meet. So the first two functions meet at -2, and the second and third function meets at +4. So we need to analyze whether these functions are continuous or not first before we can even analyze whether they are differentiable. So let's start with at x equals to -2. I'm going to start with the first function. So that's lim x approaches -2 from the negative side, because that's the first function, less than f of x equals. So all I'm going to do is sub in a -2 into this first equation over here. I'll do that in my calculator. And I get -5. Then I'll do lim x approaches -2 from the positive side. So basically, I'm subbing that -2 into the second equation. Yeah, I'll do that in my calculator. And I get -5. So since the left side and right side limit are the same, it means that the equation is continuous at x equals to -5. I mean, x equals to -2. Now, if the function was discontinuous here, we could automatically say that the function is not differentiable at -2 because it's not continuous at -2. We don't even have to calculate the slopes. But since it's continuous, we have to test for differentiability as well. But before we do that, let's test at x equals to negative, oh no, not -4, +4. So let's do lim x approaches +4 from the negative side. Remember, for +4, it's these two equations. The negative side is the top equation here. The positive side is the bottom equation here. So I'll start by subbing in +4 in the second equation here. Again, I'll do that in my calculator. Get +1. Then I'll do lim x approaches 4 from the positive side. It's basically subbing in 4 into this equation over here. And I also get +1, which means the function is continuous at x equals to 4 as well. So both our meeting points are continuous. which means we've got to test for differentiability now. In order to test for differentiability, I have to first derive my function. So I'm going to do the derivation of the piecewise function over here. Let's start with deriving this first function here. This is pretty simple derivation. 2 times negative 3 over 2 is just negative 3x, and then that's just negative 14. X is less than negative 2. For this second function, before I derive it, I want to simplify it and move the x squared to the top. So I'm going to write it as negative 32x squared plus 3. If I derive this, it will become negative 64x. Oh no, that's x negative 2. Sorry. When I move that to the top, it becomes negative 2. So this will become positive 64x to the negative 3, which is 64 divided by x cubed if you simplify that. And this is between negative 2 and positive 4. And for this third equation here, again, I'll simplify it. I'll turn this root x into a half before I derive it. 3 over 2x minus 4x to the half plus 3. If I derive this, this is just 3 over 2 minus half times 4 is 2. That's x to the negative half. And then I'll just simplify by moving this to the bottom and writing it with a square root. So that's 3 over 2 minus 2 over root x. And that's just for x is greater than 4. So now that I've derived this completely, I'm going to test for differentiability at both these points. So let's start at x equals negative 2 again. I'll do lim x approaches negative 2 from the negative side f prime x. So that's just solving in negative 2 into this first equation over here. Do it in my calculator again, although this one's pretty easy to do mentally. It's just negative 8. And then I'll do lim x approaches negative 2 from the positive side f prime x. So I'll sub it into this second function here. 64 over negative 2 to the power of 3 is also negative 8. So since the slopes are the same, it means that the function is differentiable at x equals negative 2 because it's both continuous and the slopes are identical. Let's test at x equals to positive 4. Let's do lim x approaches 4 from the negative side f prime x. So I'm solving that into the second equation over here. 64 over 4 cubed is probably, yep, that's 1. And then let's do lim x approaches 4 from the positive side f prime x. That's solving in this equation over here. So 3 over 2 minus 2 over root 4 is just 1 over 2. So the slopes are not the same at x equals to 4, which means that the function is not differentiable at x equals to 4. So this means that for this piecewise function is differentiable everywhere except for x equals to 0 and x equals to 4. If you made it to the end of this video and you found this content helpful, please hit that like and subscribe button. Thank you for watching and have a wonderful day.